about the quantum resistance, the state by me, the turning bit and so on. So let's talking about what is the quantum resistance. The quantum resistance is the cryptography algorithms that can withstand the potential code breaking attempts by the quantum computers. Also, the quantum resistance, also known by another name such as the quantum secure, post-quantum, quantum safe cryptography. So let's talking about what's the problem of the present cryptography that everybody uses in the real life. So traditionally, cryptography systems, particularly those based on the public key cryptography, rely on the mathematical problems that are hard to solve with a classical computer. Exam the factoring of the large number using in the RSA and the discrete algorithm, the classical computer nowadays also, if they want to decrypt it, it could take more than a years or maybe a billion years to solve the problem. And here comes quantum computer. The quantum computer can solve those mathematics that using RSA or the discrete mathematics. It could take only a days to solve this instead of a year unit in the classical computer nowadays. So let's recap, a short recap about the present cryptography. So the cryptography can summarize in the large type that is symmetric and asymmetric cryptography. So let's further talking about the systematic cryptography. The systematic key algorithms are the algorithm for the cryptography that use the same cryptographic key for both the encryption of the plain text and decryption of the ciphertext. The key may be the identical, or they may be a simple transformation to go between the two keys. So we can summarize that the systematic cryptography uses only the one key to encrypt and decrypt the data. So next, what's the systematic cryptography? So the systematic cryptography using a public key cryptography is the field cryptographic system that use pair of the related keys. Each key pair consists of the public key and a corresponding private keys. Key pair are generated with the cryptographic algorithms based on the mathematical problems, terms, one-way function. So we can summarize use the two keys. That is the public key and the private key. For the public key, is sent to the everyone, and the private key only for the authenticated people, such as the sender or the owner of the public key. So public key and the private key that using in the asymmetric cryptography can verify each other that is the part of it or not. So let's deep down about the asymmetric algorithm that using in the ISA, that the method that we use a lot in the present. So the ISA or asymmetric cryptography generate the key by using find two large prime number and manipulate or the multiply into the one value that that is the public keys. So the prime number that is the original of the public key, we can calculate as the private key. Let's talk about how the quantum is really decrypted. So first, you need to know about the characteristic of each computer. For the classical computer, it can only represent only or one bit in the same time, but for the quantum computer, it can represent 0 and 1 bit in the same time. From these characteristics, we can say that for the one quantum qubit can represent the two values. So, what if we have much more than about the one quantum qubit? In this example, let's talking about how about 12 quantum qubits can represent. It can represent total 4,096 values. So the quantum computer not only have a 12 qubit, but it can have all the thousands or million qubits in the quantum computers. So not only the characteristic of the quantum, only thing that can help it solve the mathematics that we use for encryption nowadays. The important thing that is the key for the quantum computer can solve it is the Shor algorithm. Because of the quantum computer can sufficient apply the Shor algorithm. The Shor algorithm is a quantum algorithm for the finding the factors of the integer. So you can just solve what's about the classical computer. Can you solve? The answer is no. The classical computer can use Shor, but not sufficient much as the quantum computer. So the superposition that we're talking about in the previous slide is quantum can represent 1 and 0 in the same time. Not only the quantum superposition, the quantum has the quantum engagements, so state of one qubit instantaneously influence the state of the another, no matter the distance between them. So let's take a deep dive into the Shor algorithm. After we got the public key or the multiplier of the two prime number, in this case we'll call it n number. So first step, we will pick a random number a that is less than the n and greater than 1. After that, you take it into the step 2, that you compute the GTS common devices or the GCD. We will find the GCD of the a and n. If GCD of the a and n is greater than 1, it means it share a factor with n. So after that, we will go to the step 3. That is the quantum period findings. We will apply the quantum operation to find the period of the function a exponent of x mod n. This step is where the quantum computer take the advantage of this Shor algorithm. So the period is related to the order of the modulo n. If is even an a exponent by mod divided by 2 not equal to minus 1 mod n, then the process to the next step, another which go back to step 1 and choose a new a. So after we find the period of r, we will go to the step 4, that is the compute of the factors of n. Using the found period of r to calculate the GCD of a exponential by r divided by 2 plus 1 and n, and the GCD of a exponent by r divided by 2 minus 1 and n. If either of these GTS common divisor is not trouble, in this example not 1 or n, then the factor of n can be obtained from these non-trivial divisors. So for the summary, a Shor algorithm utilises both the classical and quantum computations. The classical part is involving choosing a random number n, compute the GDC, and interpreting the result of the quantum period findings. And for the quantum part, quantum period finding or the step here leverage the superposition and the integrament priority of the quantum mechanic to the efficiency find the period r of the modular exponential function, which is the key to the factorized n. Once the period r is found, the classical computation is used to divide the factor of n. So in summary, quantum computer coupled with the algorithm, right, the Shor algorithm, have the potential to break widely used cryptographic schemas. Necessitating the development and adoption of the quantum resistant cryptographic algorithm to ensure the security of the sensitivity information in the future. So
What what the solution to prevent the quantum coupling to the decrypt our data using public key and private key? For the National Institute of the Standard and Technology or NIST has been leading effort to develop the quantum resistant cryptographic algorithm. Two is the post-quantum cryptography standard projects. First is represented by the four algorithms. For the first one is the crystal of Kuiper. It's a key to encapsulate the mechanism or the KEM based on the hardness of the problem in the lecture-based cryptography, such as a learning with error or the link learning with error problem. So the second one is the crystal algorithm. This is a digital signature schema based on the latest technique, providing the security against the quantum attack. And the third one is the Falcon. Falcon is a digital signature schema based on Falcon signature algorithm. It falls under the category of the lecture space too. So, and the first one is the Sphinx Pass or the So next is the last one or the Sphinx Pass, or it called the stateless hashback signature schema pass. In this stateless hashback digital signature schema is improved version of the original Sphinx schema, which is known as the robustness and the resistance against the quantum attack. So we can summarize it into two categories. The first one is the algorithm 1 to the algorithm 3 is based on the algebraic lectures. And for the last one is based on the stateless hashback signature. So let's take a deep dive into the lectures. So in the lectures, we will give the vector 1 and the vector 2. These represents the basis vector of these lectures. This vector defines the smallest repeating unit of the lecture structure and can be used to generate the entire vectors to the linear combination. And for the task that give a vector 1 and vector 2 to find the code to the lead point is instead of the code is vector problem or CVP, which is to find the lecture point and near it to the give the target point. In this case, the lead dot. So the CVP is a well-known problem in the computational math and is widely considered to be the computation difficult, make it good a candidate for the PQC because it's believed that it's resistant to the attack by the quantum computer. So you will be tasked with the find the integer m and n such that the latest point you can find them multiplied by m or the unit of the v1 plus the n, that's the unit of the v2, is as close as possible to the lead point. This is a simplified representation in the practice lecture-based cryptographic system operate in the high-dimensional and involving more than complex mathematics. So for the private and the public key using the lecture space. For the private key basis is represented by a short and nearly orthogonal vector, which is typical for ensure the lecture-based schema. The short and move orthogonal, the vector the hard is for the attacker to find the exact lecture point corresponding to the private key due to the difficult of the problem like the short is the vector problem and the close vector problem. And for the public key basis, on the other hand, is represented by the longer and the less orthogonal vector. This would be a divide of the private key to the sum transformation. This adds the structure noise, make it secure yet functional for the encryption or the digital signature purpose. Despite the public key basis, applying the last secure the structure and the mathematics of the lecture ensure that it is the computationally infeasible to divide the private key from the public key. So the asymmetric between the hard problem from attacker of the finding the short basis of the private key from the long basis the private key, which is presumed to be the hardest event for the quantum computer. So we see how the lecture space encryption and decryption the data. So for the public key encryption on the left, you have the message, in this case hello world, which you want to encrypt it. using the public key. You encrypt the message, the process involving the mathematical operation with the latest structure, like the transform the message into the form of that can be secure transmit. The number of 0, 2, 4, or 6 eggs might be represent some part of the encryption data or related noise added to the encryption. So the transmit of the potential error. The encrypted message can be transmitted over the public channel. During the transmission, error can occur, represented by trash can icon limit the error. However, the cryptographic schema is designed to tolerate and central level of the error. And for the private key decryption on the right, the decrypted message is received and decrypted using the private key. Despite a shortened and late vector label v2, the private key lecture structure is optimized for the disk processing, making a decryption feasible for the intended recipients, but infeasible for anyone not in the possession of the private key. After that, the message quality after the decrypt with the private key, the digital message hello is well recovered. So let's talking a short summary of the hash band or the Sphinx 56. So for the Sphinx 56 is the combined of the three. That is the hash key and the field time signature and the hypertree structure. And for the hash key or the market trees, this is the fundamental component where the leaf represent data block, and each non-leaf node is the hash of the chain. The market tree allows the efficient of the secure verification of the content in the large body of the data. For the field time signature, these are the signature schema that can securely sign a limited number of the message with the single key. In this context of the Sphinx 56 is the involving the using the multiple one-time signature or the OTS key. That are exposed for the signing only a few times before they are repeated. And for the hypertree structure is the combine of multiple layers of the market tree, enhancing security and supporting the generation of the large number of the signature with a single key. Each layer of the hypertree is a few times signature is used. So for the Sphinx 265 work by the generate the large and finite number of the one-time signature and arranging them into the hypertree structure. The use of hypertree allows the schema efficiently sign the multiple message, which one key pair without need to regenerate key frequently. So in the practical, the message is the sign with the Sphinx 256. Is a one-time signature is produced, and the Markov proof is generated to prove the authenticity of the signature. This proves the tie of the one-time signature to the public key and assign it to the hypertree layer. Because of this design, these Sphinx 256 signature are relatively large compared to the traditional schema, but they prove strong security guarantee in the era of the quantum computing. It is designed to be the practical and secure signature schema even against the adversity of the quantum computation. So that's all for me today. Thank you.